Hi, Dr. B. Shanmuka, Assistant Professor, Department of Mathematics, PSC, Mandya. Dear students, last class we have studied limit of a complex function, differentiability of complex function and continuity of the complex function, and using those analytic functions and using those properties we derived Cauchy's Riemann equations in both the Cartesian form and polar form. So, I just give that one note. This is essentially remember the necessary conditions for f of z to be analytic are dou u by dou x is equal to dou u by dou y and dou u by dou y is equal to minus dou u by dou x. These two relations are called Cauchy-Riemann equations. These two relations are necessary conditions for any complex function to be analytic. And one more condition that the sufficient condition for f of z to be analytic are four partial derivatives dou u by dou x, dou u by dou y, dou u by dou x and dou u by dou y must exist and must be continuous at all points of the region of the complex plane. Now, using this, so we have to see that one example, simple example. F of z is equal to real part of z. F of z is equal to real part of z is whether analytic function or not. That we have to take on that any function f of z is equal to real part of z. Real part of z means then real part of z, you know that just it is x, and this if you take that real part is x and imaginary part is 0. Real part is x and imaginary part is 0. Then find these necessary conditions, that is dou u by dou x is equal to 1 and dou u by dou y is equal to 0. If I differentiate this with respect to x, you get that 1 and this with respect to y gives that 0. In the case of v, dou v by dou x is equal to 0 and dou v by dou y is equal to 0. Just we observe from four relations here, dou u by dou x is not equal to dou u by dou y and dou u by dou y is not equal to dou u by dou x. Therefore, CR equations, necessary condition CR equation is not satisfied. So, therefore, f of z is equal to real part of z is not analytic function. Similarly, in the case of f of z is imaginary part of a complex function, that is y is also not analytic function. Then by seeing this statement that property 1, this is essential property in the complex analysis, the real and imaginary parts of an analytic function f of z is equal to u plus iv in some region of the z plane are solutions of Laplace equations in two variables. Laplace equations in two variables for u and v is dou square u by dou x square plus dou square u by dou y square is equal to 0. Here u satisfies two-dimensional Laplace equation and also v satisfies two-dimensional Laplace equation. And in this case, by the statement itself, f of z is equal to u plus iv is an analytic function. That given statement is f of z is equal to u plus iv is analytic. If this f of z is analytic, then we know that a necessary condition by CR equations we have, dou u by dou x is equal to dou v by dou y, that I can take it as 1, and dou u by dou y is equal to minus dou v by dou x. Using these two relations, that we know that from the CR equation dou u by dou x is equal to dou u by dou y and dou u by dou y is equal to minus dou u by dou x. Now, differentiate 1 with respect to x. So derivative of with respect to x means, you know, dou u by, if u is a function of x and y, u is a function of x and y, definitely dou u by dou x is also function of x and y, and dou v by dou y is also function of x and y. Therefore, it is dou square u by dou x square is equal to dou square v by dou x dou y. I call this one as 3, and here just you have to take that we are operating with respect to x on both sides, we get this one. Similarly, differentiate 2 with respect to y. That here also dou square u by dou y square is equal to minus, that is minus dou square v by dou y dou x, then you call it as 4. Just you simply observe that on RHS of these two equations 3 and 4 is a mixed derivative, that is v is differentiated first with respect to y and then with respect to x. Here that v is differentiated first with respect to x and then with respect to y. By the partial derivative property, we know that the mixed derivatives are always equal. Dou square v by dou x dou y is equal to dou square v by dou y dou x. Therefore, if both are equal means, then if I am adding 3 and 4, this is having opposite sign, therefore these two will get cancelled. Then adding 3 and 4 which gives, adding 3 and 4 which gives that dou square u by dou x square plus dou square u by dou y square is equal to 0. Dou square u by dou x square plus dou square u by dou y square is equal to 0. Therefore, u satisfies two-dimensional Laplace equation. Hence, u is harmonic function. Hence, u is harmonic function, because at any real valued function of two independent variable x and y satisfies two-dimensional Laplace equations, then that real function is known as harmonic function. Then similarly, to get that v to be an harmonic function or satisfying the two-dimensional Laplace equation, differentiate 1 with respect to y. Differentiate 1 with respect to y. Therefore, I can take this first and then this next. That for dou square v by dou y square is equal to dou square u by dou y dou x. I call this as 3, 4 and 5. I can take this one as 5. And similarly, differentiate 2 with respect to x. 2 with respect to x. That is dou square v by dou x square is equal to minus dou square u by dou x dou y. Here I just made this change, then I take that minus sign here and then I differentiate this with respect to x. So, I got this one. Now, similarly, as I told in the previous case, just you have to add 5 and 6. Since these two mixed derivatives are same, therefore, while adding these two equations, the RHS will become 0. Therefore, I got this dou square v by dou x square plus dou square v by dou y square is equal to 0. So, here observe that here both real and imaginary part of a complex function f of z is equal to u plus iv is analytic function, and this real and imaginary part satisfies two-dimensional Laplace equations, or u and v are solutions of that Laplace equations in two variables. Just I mentioned all the derivatives here, then we can get that. So, therefore, if that is this case, thus both functions u of x comma y, v of x comma y, that is real part and imaginary part of a complex function, satisfies Laplace equations in two variable. For this reason, they are known as harmonic functions or conjugate harmonic function of a complex function. Then in the same case that we have to consider the same result for the case of polar form. Polar form is if f of z is equal to u of r comma theta plus I v of r comma theta is an analytic function, then show that real part u and imaginary part v satisfies Laplace equations in polar form. So, Laplace equation in polar form I have given here. So, that equations simply Laplace equations in polar form, we have that for u and v, we have two cases. Laplace equations in polar form is dou square u by dou r square plus 1 by r dou u by dou r plus 1 by r square dou square u by dou theta square is equal to 0. That is, u satisfies Laplace equations in polar form of two variables, and similarly dou square v by dou r square plus 1 by r dou v by dou r plus 1 by r square into dou square v by dou theta square is equal to 0. That is, v satisfies two-dimensional Laplace equation in polar form. Then again f of z is analytic, means then we have f of z is equal to u plus iv is analytic in polar form. We have that CR equation in polar form is CR equations in polar form, we have this result. The polar form CR equation is dou u by dou r is equal to 1 by r into dou v by dou theta, you call it as 1, and dou u by dou theta is equal to minus r into dou v by dou r, you take this one as 2. Now, I have to first I would like to find out that u is satisfies two-dimensional Laplace equation. For this, I differentiate this one, differentiate 1 with respect to r, differentiate 1 with respect to r. Here also, since u and v are function of r and theta, therefore, their corresponding derivatives are also functions of r and theta. Here we are differentiating with respect to r, therefore, you are having two terms, 1 by r and dou by dou theta. Since dou by dou theta is also function of r and theta, so we need to differentiate here by product rule. That is, dou square u by dou r square is equal to 1 minus 1 by r square into dou v by dou theta plus 1 by r into dou square v by dou r dou theta. So, I differentiate first 1 by r, it is minus 1 by r square, and dou by dou theta is constant, I keep that one, plus this is constant 1 by r, and differentiate this with respect to r, we get this relation. I can take this one as 3, and again differentiate 2 with respect to theta. Differentiate 2 with respect to theta means here you observe that dou by dou theta is there is equal to minus r, when with respect to theta partially that r is constant, and dou by dou r is also function of r and theta, therefore, you differentiate dou by dou r with respect to theta. That is, dou square u by dou theta square is equal to minus r is constant, therefore, differentiate dou square v by dou r, that is dou theta into dou r, that is I can take that 4. Now, here to have to bring in this equation, replace in dou by dou theta, replace in dou square v by dou r by dou theta, so that I can get that the relation in terms of u. For that, I have to simplify this one, because in the partial derivative we know that dou squared by dou r dou theta is always equal to dou squared by dou theta dou r. So, using this result, I can replace this by minus 1 by r into dou square u by dou theta square, and dou v by dou theta I can get that from equation 1. So, from equation 1 I can replace dou v by dou theta is equal to r into dou u by dou r. This is replaced by r into dou u by dou r, and this is replaced by just that I have to take and dou square v by dou theta dou r is equal to minus 1 by r. So, if I replace these terms, and then we are going to see that I get that minus 1 by r square minus 1 by r square. From 1 I get that dou v by dou theta is equal to r into dou u by dou r, that is from CR equation, plus 1 by r into just observe 1 by r into dou square v by dou r dou theta can be obtained from this relation, that is from minus 1 by r into dou square u by dou theta square. Just I repeat once again, here you have to observe I want to replace this 2 in terms of u with respect to r or u with respect to theta, that is from this relation I can change this one into r into dou u by dou r, just I replace here. And again I want to replace this one from this expression, I can find out minus 1 by r into dou square u by dou theta square. So therefore, if you simplify this, I can get this result as minus 1 by r into dou u by dou r minus 1 by r square into dou square u by dou theta square. So this is what to take on that. Here dou square u by dou r square is equal to minus of this one. Then you bring this to LHS, I can get this relation like this. See, I have to bring all the terms to here and can get that this term as plus 1 by r into dou u by dou r plus 1 by r square into dou square u by dou theta square. This is equal to 0. So now just see that this is an equation, this is a Laplace equation in two variables, that is in the polar form. Therefore dou square u by dou r square plus 1 by r dou u by dou r plus 1 by r square into dou square u by dou theta square. Therefore u satisfies two-dimensional Laplace equation in polar form. Therefore, as that in the previous case, any real valued function satisfies Laplace equations in two variables, then such function is known as harmonic function. Therefore, u is a harmonic function. Similarly, I can get that for the other case, that v is also harmonic, means I have to take this term. So here from 1 I have to change this one, dou v by dou r, that is I can take that dou u by dou r is equal to minus 1 by r into dou u by dou theta, and then from this case dou u by dou theta is equal to r into dou u by dou r. Differentiate this with respect to r and with respect to theta and follow this same condition, I can get the result as in the form of this one. So that is I can write this term, this is 1, from 1 I can write dou v by dou theta, that is equal to r into dou u by dou r. This is I can write that from 1 we get this one. I can take this one as 5. I can get this one as 5. Then I can write this one. From this case, I can get that dou v by dou r is equal to minus 1 by r into dou u by dou theta. This you can take that 6, and then observe that if I am differentiating this with respect to theta, I can get that r into dou square u by dou theta dou r. And here if I differentiate this with respect to r, then I need to differentiate this by product rule, as I said that in the previous case. Then after simplification, this one I guess just mentioned here derivative of this function, differentiate with respect to r, I can get this one. If I differentiate this function and differentiate with respect to theta, I can get this one. Now replace dou v by dou r, that in the previous case I replace dou u by dou theta and dou square u by dou r by dou theta by using that this relation, and then by CR equation I can get that dou square v by dou r square plus 1 by r dou square v by dou r square plus 1 by r into dou v by dou r plus 1 by r square into dou square v by dou theta square is equal to 0. So observe here, U satisfy two-dimensional Laplace equation in polar form, V satisfy two-dimensional Laplace equation in polar form. Therefore, both U and V are harmonic function even in polar function, in polar form also. Now, after seeing this one, U and V satisfies Laplace equation, or U and V are the solutions of Laplace equations. Now, we have to see that orthogonal system of the function. Orthogonal system of function is two curves are said to be orthogonal to each other when they intersect at right angles at each of their point of intersection. That means that each point that two families of curves at each point intersect at right angles at each of their point of intersection. So, this is orthogonal system. Therefore, here property is saying that statement of this property is if W is equal to f of z is equal to u plus iv be an analytic function, then the family of curves u of x comma y is equal to C1 and v of x comma y is equal to C2 form an orthogonal system. As usual, that f of z is analytic function means then we need to consider CR equation. So, if we have CR equation, if I take that, and we have observed that families of curves means real part and imaginary part of this analytic function gives two families of curves with respect to x and y, and this y is also function of x and y. In that case, this by the application of the partial derivative, we are proving this statement as follows. So, by CR equation we got that dou u by dou x is equal to dou v by dou y and dou u by dou y is equal to minus dou v by dou x. Now, CR equation are getting, and one of the family of curve is the two families of curves is given as u of x comma y is equal to C1 and v of x comma y is equal to C2. These two families of curves we have, and here by the application of partial derivative differentiate with respect to x, differentiate with respect to x, and we know that by the total differential property that I can get that dou u by dou x plus dou u by dou y. Since y is function of x, therefore I can get that dy by dx is equal to 0. It is the property of total differential property we are studied in the partial differential calculus. Then differentiate u with respect to x and differentiate u with respect to y, since y is a implicit function of x, therefore dou u by dou y dy by dx. Here dy by dx is equal to minus dou u by dou x divided by dou u by dou y. We know that geometrically dy by dx represents slope of the curve. Therefore, I can take that this is a slope of the curve, this family of this curve u of x comma y is equal to C1. So, this I can take it as 1, that I can take that 2 if I take this one as 1. Then similarly, this I got it dy by dx is a slope of a curve means dy by dx the slope is represented by a notation m1, I can get this result. Similarly, we have to differentiate this with respect to x, we can get that dou v by dou x plus dou v by dou y into dy by dx is equal to 0. That is, differentiate v with respect to x and v with respect to y, but y is an implicit function, therefore dy by dx. And here you simplify this for dy by dx, dy by dx is equal to, that is minus dou v by dou x divided by dou v by dou y, dou v by dou y, and this is again geometrically represents slope of the curve. Therefore, dy by dx is the slope of this curve at any point, that I can take that as a simple notation m2. Now, take the product of these two, I can take this one as 3. Now, take the product of 2 and 3, see that what is that we are going to get from this relation. So, clearly mention that differentiate both the families of curves with respect to x, I got these two results. From these two results, we get this following expression. m1 into m2. If I take the product of these two slopes, I can get that this is equal to minus dou u by dou x divided by dou u by dou y. I think that is taken into minus dou v by dou x divided by dou v by dou y. Then minus will become plus because product. Then by using CR equation, we see that this result gives what? By using CR equation, either you can replace dou by dou x, dou by dou y, or you can replace dou by dou x and dou by dou y in terms of x. That any one of that possibilities you can take chance that I can take that dou u by dou x is equal to dou v by dou y divided by, and dou u by dou y is equal to minus dou v by dou x. It is minus dou v by dou x. So now just I replace dou u by dou x and dou u by dou y by using CR equations. That gives dou v by dou x divided by dou v by dou y. Just you see that common terms will be get cancels each other. That is dou v by dou x get cancels, and dou v by dou y and dou v by dou y get cancels. Then what is that? Here minus and this one, therefore I can get that minus. Then m1, the slope of two curves, or that the slope of two curves gives that product of two curves, slope of the product of two curves gives minus 1 means this forms orthogonal system. This forms orthogonal system. That is, simple proof I follow this. You can see that this gives that this m1 into m2 is equal to minus 1 form an orthogonal system. This is one of the case that we have seen that if this is valid means then we can also have that in the polar form also we can get that orthogonal property in the form of polar curve. In polar curves we have seen that CR equations in polar form is very simple, that I can get this one. Now CR equations in polar form, it is dou u by dou r is equal to 1 by r into dou v by dou theta, dou u by dou theta, and dou u by dou theta is equal to minus r into dou v by dou r. Now these two are CR equations in polar form, and we have that families of curves in polar form, that is u r comma theta is equal to C1. It is the families of curves form the real part of an analytic function. Then I can take this one as 1. This is an imaginary part of analytic function v of r comma theta. V of r comma theta is equal to C2. So see that two families of curves, and one is from real part and another one is from imaginary part, and in this case also u is a function of r and theta and r is a function of theta. That is in polar form r is always function of theta. Differentiate 1 with respect to theta. Differentiate 1 with respect to theta means theta is the independent variable, r is the dependent variable. Therefore, in this case dou u by dou r, that is dou u by dou theta plus dou u by dou r into dr by d theta, that is equal to 0. So dou u by dou theta plus dou u by dou r dr by d theta is equal to 0, because r is function of theta. Therefore u with respect to r means keeping theta as constant, and r is with respect to theta means it is ordinary derivative. Therefore dou r by dou theta is equal to minus dou u by dou theta divided by dou u by dou r, and this I can take that 3. From this I can, after simplification, we can get that dr by d theta is equal to minus dou u by dou theta divided by dou u by dou r. And one property you know that in the polar form, the angle between the radius and the tangent of the curve, that is tan phi 1 I can find out for the family of this curve, that is r divided by dr by d theta. Dr by d theta. This is phi 1 being the angle between the radius and the tangent to the curve 1. That is, I can take that phi 1 is that angle between the radius and the tangent to the curve 1 at any point p of r comma theta. So, use this result there, I can get that tan phi 1 is equal to r divided by minus dou u by dou theta divided by dou u by dou r. So, just I transform this to there, and after simplification, that is, you take that this goes to numerator, and therefore, I can get that this result as tan phi 1 is equal to r into dou u by dou r divided by minus dou u by dou theta. You take this one as 4, this one as 4, that is 4 means that is 3 and 2 means then okay 3, I can take that number may be missing, and even then I can get this. Now, similarly differentiate 2 with respect to theta. Differentiate 2 with respect to theta means what that I can get, just see that differentiate 2 with respect to theta. Now, differentiate 2 with respect to theta, that is dou v by dou theta plus dou v by dou r into dr by d theta, that is equal to 0. So, here dr by d theta is equal to dr by d theta is equal to minus dou v by dou theta divided by dou v by dou r. So, now dou r by dou theta, if we know that means, then we can find out tan phi 2, that means that I have to take that tan phi 2, that is that angle between the radius and the tangent to the curve 2, tan phi 2 I can take that, I find that tan phi 2 is equal to r divided by dr by d theta. So, r divided by dr by d theta means, then substitute this one, I can get this as tan phi 2 is equal to, so tan phi 2 is equal to, you bring this to here, and then this term goes to numerator, that gives, that is r into dou v by dou r divided by minus dou v by dou theta. You take this one as 4. As similar as what I did for the case of tan phi 1, here also you have to follow the same procedure. I put here, and then this goes to numerator, and finally I got this result, tan phi 2 is equal to r into dou v by dou r divided by minus dou v by dou theta. Then these two, if I get that, we have one relation, the product of tan phi 1 and tan phi 2, if you consider, see that what is the result which we are going to get that. So, tan phi 1, tan phi 2 and their product which we are going to take like this, tan phi 1 into tan phi 2. So, tan phi 1 into tan phi 2 means this minus and this minus will become plus, and then I can get that r into dou u by dou r divided by dou u by dou theta, that is minus, if you want you can write r into dou v by dou r divided by dou v by dou theta minus, this minus and minus will become plus. So, therefore, this gives r square into dou u by dou r divided by dou u by dou theta into dou v by dou r divided by dou v by dou theta. Now, you can take that dou u by dou r will be replaced by using CR equation, and then see that what is the term we are going to get that. So, dou u by dou r is 1 by r into dou u by dou theta, and dou u by dou theta is equal to minus r by dou u by dou r. Just you replace by using CR equation. Just you replace by using CR equation. Where CR equation is this one, so therefore I replace this term, which gives that tan phi 1 into tan phi 2 that is equal to, then what is that, r square into dou u by dou r is equal to 1 by r into dou v by dou theta, that is divided by dou u by dou theta is equal to minus r by dou v by dou r. So now I got that this term, and remaining term is dou v by dou r divided by dou v by dou theta. So now I use that CR equation, and this term is replaced to this, and this r square get cancelled, then this r and r get cancelled, then du by dou r and dou v by dou theta and dou v by dou theta get cancelled, that is minus 1. Observe here r square r get cancelled, then again it is 1 by r, and then dou v by dou r and dou v by dou theta is get cancels each other. I got the tan phi 1 into tan phi 2 is equal to minus 1, and this relation forms orthogonal system of a families of curves. Orthogonal system of family of curves, we have observed that the converse of the both the properties need not be true, but tan phi 1 is equal to r by dr by d theta, phi 1 being the angle between the radius and tangent to the curve 1, that's just I discussed on the board. You have observed that. Then finally I got this result. So this result forms an orthogonal system. Now that we pass on to the one more property, that is, suppose we know that a complex variable z is equal to x plus iy, then its complex conjugate is z is equal to z bar is equal to x minus iy. So now simplify this one, I can get that x is equal to 1 by 2 into z plus z bar, and simplify for y, I can get that 1 by 2i into z minus z bar. Now consider a complex function f of z, that is in terms of u of x comma y is a real part plus I into v of x comma y. Now replace x and y, that what the value which we got from this complex variable and its complex conjugate, this x and y, you replace here, x is replaced by z plus z bar by 2 comma z minus z bar divided by 2i. Similarly we get that. Now if suppose that complex conjugate and its complex number is having same value, that means z is equal to z bar, I got that result f of z is equal to u of z comma 0 plus I into v comma v of z comma 0. Just you have to observe equation 1 and 2. Equation 2 is same as 1 if you replace x by z and y by 0, and here x by z and y by 0, I can get that this one. This is due to Milnes-Thomson. Therefore Milnes-Thomson is that similarly in the polar form we replace r by z and theta by 0 in the polar function f of z is equal to u of r comma theta plus I into v of r comma theta. This is both the cases, that is we are going to have that from that is due to Milnes-Thomson method. Milnes-Thomson method says that for any complex function, just any complex function, just to replace x by z and y by 0 and r by z and theta by 0, we can get that. So we have learned that properties of that harmonic functions property and orthogonal system of the curves, orthogonal properties, and now we have to find out that analytic function, any complex function which is to be analytic means then we have to verify the necessary conditions of CR equations and then find out. To solve the problem, I use these identities. So one of that is sine of ix is equal to I into sine hyperbolic x, or sine hyperbolic x is equal to 1 by I sine ix, cos of ix is equal to cos hyperbolic x. So using this property, one of that example I considered here, show that f of z is equal to sin z is analytic and hence find its derivative. So and hence find its derivative means then I have to take this example and see that any function is said to be or is analytic, then necessary condition should be satisfied by that function, that is f of z is equal to sin z, f of z is equal to sin z. Then I can take that u plus iv is equal to sin of x plus iy, because you know that z is a complex variable. I can take that x plus iy. Now I have take this function. I want to find out this function whether it is analytic or not analytic. And for that case, I have to determine real part of this function and imaginary part of this function, and see that this real part and imaginary part satisfy the necessary condition of CR equation. So now this I can write by using sin A plus B means sin x into cos of iy plus cos x into sin of iy. Now I just shown that identities of the function sin x into cos hyperbolic y plus I into cos x into sin hyperbolic y, because sin of ix is equal to I into sin hyperbolic y. Cos of ix is equal to cos hyperbolic y. I use these results in these terms, and then I got this one. See that the RHS of this term here, it is a real part and this is a imaginary part. Then this is real part and this is imaginary part, means then I can equating real and imaginary part, equating real and imaginary parts. So here the real and imaginary part means I can get that equating real part means u is equal to sin x cos hyperbolic y and v is equal to cos x sin hyperbolic y. Now here the real part is this one and imaginary part is that, and now we have to see that, take that number 1, number 2 if you want that, 1 and 2. Now to find out necessary condition CR equation, differentiate 1 with respect to x and 1 with respect to y. The derivative of u with respect to x is equal to cos x and y is constant, therefore cos hyperbolic y, and derivative of this u with respect to y. Now differentiate u with respect to y, this gives that sin x is constant and derivative of cos hyperbolic y is sin hyperbolic y. Similarly, you differentiate this with respect to x and this with respect to y, that is dou v by dou x, differentiate v with respect to x, which gives that derivative of cos x is minus sin x into sin hyperbolic y. Again differentiate v with respect to y, that is dou v by dou y, that means v with respect to y means keeping x as constant, therefore cos x into sin hyperbolic y. So from these four relation, dou u by dou x is equal to cos x cos hyperbolic y, that is equal to dou v by dou y. I clearly mentioned once again, dou u by dou x is equal to cos x cos hyperbolic y. Then cos x cos hyperbolic y means, then what is that, dou u by dou x is equal to dou u by dou y. It is with respect to y means, sorry, this is cos hyperbolic y, cos hyperbolic y. Dou by dou y is cos x is constant, differentiate sin hyperbolic y, it is a cos hyperbolic y, dou by dou y. So dou u by dou x is equal to cos x cos hyperbolic y, and this I can get the dou by dou y. So therefore this satisfies dou u by dou x is equal to dou v by dou y. So these two relations are satisfying this condition. Then again for this condition, what is that I am going to get that? Dou u by dou y is equal to sin x sin hyperbolic y. This gives that minus sin x sin hyperbolic means that is minus dou v by dou x. So these two relations satisfies this relation, clearly mentioned dou u by dou x and dou by, these two satisfies the first relation and these two satisfies the second relation, and this real and imaginary part satisfies CR equations, CR equation. Hence f of z is equal to sin z is analytic. See that the necessary conditions of the CR equation, that is necessary condition CR equation satisfied by this sin z function, therefore it is analytic function. So to find out the derivative, I take that one of the derivative form. You know that f dash z is with respect to x, I can take that dou u by dou x plus I into dou v by dou x. This we have derived in the derivations of Cauchy's Riemann equation. After analytic property, differentiable property, we use this one. Now, by this expression, this gives cos x cos hyperbolic y. Dou u by dou x is replaced by this plus I into dou v by dou y is equal to, that is dou v by dou x is equal to minus sin x into sin hyperbolic y. So dou v by dou x is equal to this one, and then simplify this. See that what is that, I can get that. See clearly from the derivative I replace dou u by dou x and I replace dou v by dou x, which gives this one, and again I use the property cos x cos of iy minus I into sin x into sin hyperbolic y is 1 by I into sin iy. I mentioned this in the identity. This gives that I get cancelled. Then cos x into cos iy minus sin x into sin iy. Therefore, cos a into cos b minus sin a into sin b, which gives that cos of x plus iy. Therefore, this gives that cos z. Then f dash z is equal to cos z. I can call this one as 1 because I want to use that Milnes-Thomson method. Therefore, I can find out this one. So this gives d by dz of f of z is equal to cos z. Therefore, d by dz of sin z is equal to cos z. So derivative of sin z with respect to z is cos z, and observe that in ordinary differential calculus, just you replace x by z, which gives that the derivative in terms of complex variable. So another way we can find out this is here itself by using Milnes-Thomson method, or from that up to this one, this problem will be completed. And now this can also be obtained because most of the case if we use this one, very simply we can get that result. Replace x by z and y by 0. If I replace this one, I can get that f dash z is equal to cos z into 1 minus 0. Sin z into sin 0 is 0, therefore both are 0. That is also given cos z. Cos z means f dash z is equal to cos z means then same property which means that this is by ordinary method we can find out. Then by using Milnes-Thomson method we can also find out the same derivative function. This is the one of the function. One more function I have mentioned here. F of z is sin z, and also found that f dash z is having cos z, and this is the function what I have did on the board that written here. Now show that w is equal to z plus e power z is analytic, hence find dw by dz. Similar way, w is equal to f of z, you have to find out this real and imaginary part of that. The real part of this is x plus e power x into cos y, and imaginary part is y plus e power x into sin y. So these two also satisfy CR equation, and then using the same property dou u by dou x plus I into dou u by dou x. Dou u by dou x means differentiate this with respect to x, I can get this one, and differentiate this with respect to x, I can get this term. So it is simplify this one, 1 plus e power x into cos I plus I sin y, again that e power I y. So e power I into e power x is equal to e power I plus I y therefore it is e power z. So again here also you replace y by 0 and x by z means e power z into cos 0, this is 0, therefore I can get this term. And one more example is that then I will take up this in next class. So these are the today's class. We have solved that 3-4 problems and one property that I have to continue this one in next class.